So in the previous videos we discussed about how to prove a particular language is not regular by using pumping lemma. Okay, so that is one of the method to check whether a language is regular or not. Okay, without using pumping lemma also we can check whether a particular language is regular or not. So in this video I am going to explain you how to check whether a language is regular or not without using pumping lemma. Okay, so we can take some examples and we can check whether it is regular or not. So one problem, L equal to a power n such that n greater than or equal to 1. Is it regular or not? If it is regular, if a language is regular, then definitely we can draw a finite automata and we can represent by using a regular expression. If you are able to draw a finite automata or if you are represent by using a regular expression, then that particular language is definitely regular. And you already know that every finite language is regular. Every finite language is regular. Okay. All the finite languages are regular languages. If the language is not finite, then you need to check whether you are able to draw the finite automata or whether you are able to represent it by using a regular expression. So what is regular expression? It is a mathematical representation of a regular language. Okay. So see, a power n. So a power n means n value is greater than or equal to 1. So a power 1, a power 2, a power 3, a power 4, right? So from this, are you able to draw a automata? So see here you can see a repeating pattern. First 1a, then 2a, then 3a, then 4a. So a is repeating, right? So minimum condition is 1a. So just try to draw automata for this one. Minimum 1a should accept, then any number of a's, right? So we are able to draw the automata. So definitely this particular language is regular. So this is regular. Also we can represent it by using a regular expression too. Then second thing, L equal to a power n b power n such that n less than or equal to a power 10 power 10 power 10. Okay, here you can see n is bounded. Okay, the n value is less than or equal to something. Okay, so definitely this is a finite language. Language is finite because the range of the value of the n is within this particular value. Okay, so that is finite language. So we know that every finite language is regular. So this L is a regular language. Okay, so let's see another problem. L equal to a power n b power m such that n comma m greater than or equal to 1. Is this regular or not? First you check whether we can draw a finite automata. We can create a finite automata for this one. See here n number of a's, then m number of b's. That means a and b are independent. They are not depending each other. Okay, so a and b are independent. So first we can generate n number of a's. N value is greater than or equal to 1. So minimum condition is a minimum 1a, 1b will be there because n and m should be greater than or equal to 1. So a, then any number of a, then followed by b with any number of b's. Okay, so we can draw a finite automata for this one. So definitely this language is a regular language. Okay. Next problem, L equal to a power n b power n such that n greater than or equal to 1. Here see n number of a's followed by n number of b's. If there are 10 a's, it should follow 10b. If there are 1000 a, it should follow 1000 b. If there are more 1 lakh or that much a's, then it should follow that much equal number of b's. Equal number of a's and equal number of b's. Okay, so this is not unbounded. N is greater than or equal to 1. N may be anything, right? Greater than or equal to 1 condition. So here we need to store a's and b's, n number of a's and n number of b's. We need to count a and b. We need to compare whether a and b are n a's and n b's are equal. So storing, counting and comparing is there for this particular language. If there are 10 a, it should consist of 10 b's. 10 A's followed by 10 B's. If there are 1 lakh A's, it should follow 1 lakh B's. Okay, so we need to store that much A's and that much B's. We need to count that much A's and B's. And finally, we need to compare whether the number of A's and number of B's are equal. Okay, since finite automata, we know finite automata is having finite number of states. Okay, so memory is less. Limited memory. Finite memory. Okay, so counting, storing, counting, comparing is not possible for finite automata. It need more memory. Since the memory is less for finite automata, we can't represent it by using a regular expression, or we can't draw a finite automata for this particular language. So definitely this language is not regular. Okay, so finite automata, we can't draw finite automata, we can't represent by using a regular expression for this particular language, because we need to store the number of A's and B's, we need to count the number of A's and B's, finally we need to compare whether both the count are equal. So these are not possible for finite automata, since finite automata is having very less memory. Okay, so this thing we can do for push down automata, that I will explain you in the upcoming lectures. Next is L equal to W power R such that length of the string is 2 over the input alphabet A comma B. See, W power R. So what is W here? Length of the string. Length of the string is 2. So the possible strings are AA over the input symbol AB. Length is 2, AB length 2, BA length 2, BB length 2. This is W. W power R means reverse. AA, BA, AB and BB. Okay, so W power R means AB, AB then it is reverse. AB, then it's reverse. BB. Right? So this is a finite number of strings in this language. So if the language is finite, definitely the language is regular. Okay, since every finite language is regular. Since it is bounded, that's why this is finite number of strings in the language. So we can say it is a regular language. Okay, if it is not bounded, then it is very difficult. So we can say that is not regular. So let's see with one example. L equal to W power R such that W belongs to A power B the whole star. See, suppose the length of W is this. Then the reverse will be reverse. BA, right? So depending upon the length, if the W is big length, that is infinite length string, then finite automata doesn't have the capacity for infinite length string. Okay, so finite automata is not able to store that much length string. So definitely this particular language is not regular. This is not regular. This is bounded, that's why we have finite number of strings. So we can draw a finite automata, so the language is regular. This is infinite. If depending upon the length of the string, that much length, if we are taking the reverse of that string, then it will be a big string, WWR. So the finite automata is having less memory, not that much capacity to store that much lengthy string. Okay, so so that particular language is not a regular language. We can't draw a finite automata for this particular languages. Okay, so if it is WW, L equal to WW. W belongs to AB star. This case also, if depending upon the length of W, if W is AAA, BA, then followed by the same thing, AAA, BA, right? So for that much string, we can't store for a finite automata. So this particular language is also not a regular language. See this example, A power n, B power m, C power k such that n, m, k greater than or equal to 1. So in the previous example, we saw A power n, B power m. Here you can see n number of A's followed by m number of B's followed by k number of C's. Here number of A, B and C's are not dependent. Both are independent. We can generate A, B, C independently. Okay, so there is no problem. So we can draw a finite automata for this particular language. We can represent by using a regular expression also. So how to draw finite automata? We have the minimum condition is 1, right? So n number of A, then n number of B, then k number of C. So we can draw a finite automata. So definitely this particular language is regular. Okay, if there are equal number of A's, B's, C's, then it is not regular, because storing, comparing, counting is not possible for finite automata, since finite automata is having less memory. Okay, another problem, A power I, B power 2j. Here if there is one A, there should be double B. Okay, so A star, B B, then B B star. Okay, also we can draw finite automata for this particular thing. So we can, this is a regular language. The next one, A, here A power n is n such that n is even. Okay, so A power 0, A power 2, 0, 2, 4, 6, 8, etc. are even numbers, right? Length 0, length 2, length 4. So this particular, you can see an progression here, arithmetic progression here. 0, 2, 4, 6, 8, so on. Right? You can see the common difference. 2 minus 0 is 2, 4 minus 2 is 2. Okay, so we can, there is a pattern in this particular language. Okay, common difference is 2. Right? So definitely we can draw a finite automata for this particular language. Then this language is a regular language. Similarly, in case if n is odd, A power n such that n is odd. Odd means 1, 3, 5, 7. You can see the common difference. 3 minus 1 is 2, 5 minus 3. So you can see this is in the arithmetic progression, right? So definitely this particular language is a regular language. Also prime. Prime numbers, you will not see any pattern, right? It is not in the form of an arithmetic progression. So definitely it is not a regular language. Here also you are not able to see any pattern. Here see 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9. So there is no common pattern in this particular language. If there is no pattern, you can't draw a finite automata. So definitely that is not a regular language. Okay, in this example also you are not able to find out any particular pattern. So this is also not a regular language. For this example also you will not see any pattern. If you are able to find out any particular pattern in between strings, definitely you can draw a finite automata and you can see that particular language is a regular language. Okay, so these examples are also not regular. And this is also prime. There is no pattern, so definitely this is also not regular. Here see number W, string is W. Okay, equal number of A's and equal number of B's. If there is any comparison, then definitely finite automata can't perform that. Okay, so this is not a regular language. Here number of A's and B's should be equal. If it is less than or equal to condition also there, that is also not possible. We can't compare number of A's and B's, number of this counting is not possible for finite automata. So definitely this particular language is not a regular language. Okay, but if the problem consists of mode something, here number of A and number of B equal. Number of A in the string W, number of B's in the string W are equal or less than or equal to or greater than or equal to. In this case, definitely finite automata can't perform anything. But if mode 3 operation is coming, modular counting is possible in finite automata. Okay, remainder finding. So if there is any modular counting showing in the language, definitely that particular language is regular. We can draw a finite automata for this particular language. Okay, here see A power n such that n greater than or equal to 10. So the minimum condition is 10 A's, then any number of A's. So you can draw 10 A's finite automata, then any number of A's. So this is a regular language. We can draw a finite automata for this particular language. So first you need to check whether the language is finite. If it is finite, definitely every finite language is regular. Other case, if it is not finite, that is if it is infinite language, you need to check whether any pattern existing. Okay, if there is any pattern, definitely we can draw a finite automata. We can represent by using a regular expression. Then that is a regular language. If we are not able to find any pattern, it is not a regular language, because we can't draw a finite automata or we can't represent by using a regular expression. In this case also you can see a W, then again the same string, then the reverse of that particular string. So here also storing, counting, comparing is there, right? So this is also complicated. This can be performed by using a finite automata. So the language is not a regular language. Here also you can see n number of A, n number of B, n number of C. A's and B's and C's are depending each other. Okay, so this is not possible for finite automata. This is not possible to represent by using a regular expression, or we can't draw a finite automata for this particular language. So definitely this is not a regular language. Okay, here also you can see n, then again b power n power m, then c power m. Here also they are dependent. Okay, need to store a's, then b's, then c's, and need to compare them. Right? Here a and b n number, then plus m. This also comparing with the c. Right? So this is not possible for regular finite automata. So this is the case. If the language is finite, it is regular language. If the language is not finite, that is if the language is infinite, check whether it is you are able to draw a finite automata. If you are able to find a pattern, then you can draw a finite automata and you can say that it is a regular language, otherwise not. Okay.